Welcome back. So, let us continue the discussion on turbulence and the scaling of turbulence. So, we are looking at the different scale of turbulent flow field. So, like macrostructure and then the microstructure, and then also we have looked at the energy cascading phenomena. So, now what we are looking at the different statistical description of the turbulence, and what we have done so far looked at the averaging and all this. So, now we look at some of these other features like probability density function. So, which is quite useful when we look at the any statistical signal like turbulent signal. So, this is our one of the, if you look at, this is the velocity profile and it is a time history of the velocity profile. This is instantaneous velocity profile, and now if we look at the PDF of that thing. So, we have a measured time looked at between these two velocity, like one particular instant and the delta change of that. So, using that, the PDF definition of u would become the integration of this function with du would be 1. Now, when you look at the definition based on mean based PDF, so we can get the mean velocity profile, which is u fu du. Now, we can look at some of these statistical quantities. So, first thing that we look at the variance of a velocity component. So, like u primes square bar, which will be integration over ui minus ui square f ui dui, where your ui prime is ui minus ui, and this quantity is the mean quantity, and this guy is my turbulent fluctuation. Similarly, one can find out the RMS or standard deviation. So, if we look at the RMS or standard deviation of a velocity component, which will give us ui RMS is square root of ui prime square. Now, we can find out the covariance between two velocity components. So, covariance between two velocity component at same point in space and time, at same point in space and time. So, the covariance of, let us say, ui uj, this would be ui prime uj prime, which is nothing but ui minus ui mean uj minus uj mean f ui uj dui duj. So, this function is called the joint PDF. Now, this concept of this probability density function, this should be again quite handy when we look at the some PDF based conversion model. Now, the other one is the correlation coefficient. Correlation coefficient, which is, we can say, rho ij equals to covariance of ui uj by ui RMS uj RMS. So, that give you this correlation coefficient is sort of bounded. Now, there could be some special cases what one can look at it. Let us say if we have statistically stationary case. So, in a statistically stationary case or steady turbulence, so the PDF becomes independent of time. So, then we can write F to ui equals to t plus delta t ui, where my ui mean is not a function of time, and similarly ui prime t uj prime t plus tau, that is f tau. So, that is also independent of t. Now, item for statistically homogeneous turbulence. So, we can look at the statistically homogeneous turbulence. So, for statistically homogeneous turbulence, we can write x plus delta x ui, which will get me ui mean is no more function of space, and ui prime and uj x plus delta is f of delta, which is also independent of x. So, one case independent of time, other case you have independent of. Now, for a stationary process, we can write that limit when the time goes to infinity, u bar limit un is u bar. So, that means the time averaging and the ensemble averaging, they lead to the same thing. Now, here one can think about finite integral time scale of turbulence is the. So, if you have finite integral time scale of turbulence, which means the turbulence fluctuations are uncorrelated over sufficiently long time. Now, for homogeneous process, we can have this limit, this is line averaging become similar to ensemble averaging. So, here the finite integral time scale of turbulence, here that turbulent fluctuations are uncorrelated over sufficiently long distance. So, one case the fluctuations are uncorrelated over sufficiently long time, and this case for homogeneous process the turbulent fluctuations are uncorrelated over sufficiently long distance. So, these are the two hypotheses one can have. Now, that brings to the Reynolds decomposition. So, Reynolds decomposition, what we have is that this is Reynolds who proposed in 1895, that if I have an instantaneous flow field, I can have mean plus fluctuating component. So, after Reynolds averaging, the properties that one can have, these are quite important. One is the a plus g averaging, it becomes a plus g. If you have anything multiplied with, then del f by del s, del f by del s, and f bar g. So, these are the some of these desired properties of averaging operator. Now, if you look at the time averaging, that is u prime t, time averaging actually it does not satisfy condition number 4 because of the doubling of the integral interval. For like you have time averaging over another time averaging which is 1 by t, tau goes minus t to plus t, 1 minus tau by tau u t plus tau d tau, which is not equals to, which is 1 over t, tau equals to minus t by t to t plus tau d tau. Now, however, if your t is much larger than integral time scale, which is the time scale of large eddies essentially. So, integral time scale is the time scale of large eddies. If it is much larger than that, then that case this error is small. Now, at the same time, if you look at the ensemble averaging does satisfy all these properties. So, this is what we write from ensemble averaging is that 1 by n, where alpha goes to n. So, that satisfy all the conditions. Now, we can get the Reynolds average equation for mean flow. Now, Reynolds averaged equation for mean flow. So, we start with an incompressible Navier-Stokes equation and we get this is our incompressible NS equation. This is 0 del u by del t plus uj del ui by del xj 1 by rho plus nu square and del theta by del t plus xj equals to kappa del 2 theta by square. So, this is our starting point, that means all incompressible Navier-Stokes equation. Now, we apply the averaging over here. So, once we apply averaging, Reynolds averaging to these equations, so we can get the averaged equation, and continuity equation look like del xi 0, momentum equation becomes del u by del t plus uj bar by del xj minus 1 by rho del p by del xi plus nu del 2 ui by del xj2 minus del ui del uj prime by del xj. So, that is an additional term. Now, similarly, del theta bar by del t, uj by del theta bar by del xj, kappa uj prime theta prime. So, we can see this is one term which is, and this is another term. So, compared to this starting equation or governing equations, we can see that due to the averaging we get back these additional terms, and these terms are known as Reynolds terms. Now, we can rewrite the momentum equation. So, if we rewrite the momentum equation, what we get, rho del ui by del t plus uj del ui by del xj equals to del of xj minus p per plus mu del ui bar by del xj plus del uj by del xi, and last component is minus rho ui prime uj prime bar. So, everything under that. So, this particular term is the molecular stress term, molecular stress, and this term sitting there is known as Reynolds stress or turbulent stress. So, this extra term does arise because of my Reynolds averaging over the equation system. Now, one can interpret is that the turbulent fluctuations act on mean flow as if they induce an additional stress, which direct result from the averaging, and this additional stress originates from the transport of mean momentum by turbulent fluctuation. So, this is what one can interpret it. Now, one can also physically interpret, you can have a velocity profile like this, and your fluid particle may go from here to there. Now, to do that, when you go there, your mean velocity increases, mean momentum also increases. But the between this point and this point, to maintain that momentum flux, this term has to be negative. Similarly, from this location to, and this happens is that the transport by the turbulence eddies. If you come from this position to this position, your mean momentum decreases, but to maintain the momentum, this has to be increased. So, one can look at in that way. Now, if I look at those equations completely, then this is my mean continuity equation, momentum equation, this is the Reynolds stress, this is. So, we need an equation for the Reynolds stress. Now, closer for this stress, what we can write, we have this momentum equation, we can rewrite again, rewrite the momentum equation in a slightly different form, where this would be the del sigma ij by del xj plus del xj minus rho ui prime uj prime, like that. So, sigma ij, this is the molecular stress, where it is P delta ij plus rho nu del u bar I by del xj plus del uj bar by del xi. So, this is our isotropic part, and this is the part which is deviatoric part. So, that means this is pressure stress and this is the shear stress. Now, one can again, to close that Reynolds stress term, we bring in the Boussinesq hypothesis. So, Boussinesq hypothesis. So, we apply the Boussinesq hypothesis, so that we can write this Reynolds stress term in a slightly different way. So, this is the term we can write 1/3 rho u prime k square delta I j plus rho minus u I prime u j prime plus 1/3 I j. So, this term is again isotropic part, and this is again deviatoric part. This one can think about it's a turbulent pressure, and this is your turbulent shear stress. Now, Boussinesq hypothesis based on the similarity with molecular stress, we can write this u I prime u j prime plus u k square delta I j rho nu t del u I by del x j plus del u j by del x I, and this nu t is the eddy or turbulent viscosity. Now, the scaling of eddy viscosity, and if this is the size of the turbulent eddy, which is having a velocity scale of UL, and this is the picture of the shear layer, then the eddy viscosity is order of U into L, and for the large scale it is UL, that is for macrostructure scale for the large eddies. So, which allows more efficient mixing. Now, this is an example of a free shear flow, where you see this is an mixing layer, that means two different layers they are mixing. So, different kind of eddies that form, and this is a velocity profile, this is a free jet, and this is an wake. So, these are some of these example what. Now, when you look at the round jet, as you go along with the axial distance, this is how the velocity profile actually looks like, and this is from the, so which actually gives you an idea that this is self similarity mean flow invariant of x when scaling with center line velocity. So, this is an important hypothesis. Now, one can take a planar jet. This is the jet nozzle, and this is where the jet is injected, and further downstream you can see the profile how it looks like. This is our mean center line velocity, and this is the definition of. Now, we can look at this analysis of that thing. So, we start with our, let us say, governing equation, which are in Cartesian coordinate system. This is 0, then del u by del t plus u del u by del x plus del u by del y del u by del z 1 by rho del p by del x del 2u by del x2 plus del y2 minus del u prime by del x v prime u prime by del y w prime u prime by del z. Similarly, we can write it for y momentum, and that is del v by del t plus del u by del v by del x, del v by del y, del v by del z equals to 1 by rho del y plus nu del 2 v by del x 2 del y 2 plus del 2 v bar by del z 2 minus by del x del y minus del z, and the third one would be in the z momentum. So, this is our convection term. This is the diffusion term. And these are the Reynolds stress term. Now, we can have some assumption to simplify the system and carry out this analysis. So, one of the simplification that one can do is that first of all is that it is a mean flow is 2D. So, that is the mean flow is 2D, fluid statistically stationary. So, that is statistically stationary, and third is also flow is statistically homogeneous in z direction. So, if we have these three assumption, then the flow is mean flow is 2D, that is mean flow, flow is statistically stationary and statistically homogeneous. So, this goes off, then this term goes off, this term goes off, then this is u, this is also u. So, this term goes off, this term goes off, this goes off, this goes off, this goes off, and this whole third dimension equation goes off. So, that is how we get a simplified system when you assume these things. So, now we can use this simplified system to find out the solution, and we will discuss this. So, we will stop here and discuss the solution procedure in the subsequent lecture.